this assessment asks us to draw the peak or the signal that would correspond to the hydrogens at C3 in the molecule shown. And so essentially what we're going to be doing here is working backwards from how spectroscopy is going to be used. Normally we look at a spectrum, and from that we predict what the molecule is. Here we're given the molecule, and so we're going to predict what signal we would see. The process is going to work the same. What we first want to look at is how many hydrogens are at carbon 2. That's going to be what the peak would integrate to. So we have 2 hydrogens at C3. So it's going to integrate to 2. We can look then at what we would expect in terms of its multiplicity, and we'll get the multiplicity. Usually the multiplicity will tell us about the neighbors. Here we're going to see how many neighbors, and that's going to tell us about multiplicity. And so if we look at the C3 hydrogens, the CH2 that's here, pointing, there we go. When we get to the 2, at 2, there's only one neighbor. So these 2 hydrogens only have one neighbor. The n+1 rule says that if you have one neighbor, it should show up as a doublet. So we're going to have a peak that integrates the 2 that is a doublet. In fact, we can go ahead and draw that. So it will look like that. Now, the only thing that we have left to do, and we can write that it integrates to 2. The only thing that we have left to do is to assign an approximate chemical shift. And so this C3, these 2 hydrogens, are next door to an electronegative atom. Being next door to a highly electronegative atom like oxygen is going to put those in the range of around 3 to 4. More specifically, being next to an oxygen that's part of an ester probably pushes us even a little bit further to a higher chemical shift, or more downfield, or more de-shielded. So we'll say that this is going to show up around 4.2. Around 4.2. If you said 3.6, if you said 4.5, close enough, right? So some number between 3 and 4, maybe a little higher because of the ester. This is what we would expect these 2 hydrogens at C3 to look like in an NMR spectrum. Now, obviously, we're not showing the spectrum of the whole molecule, because each of the sets of hydrogens in the molecule would give their own signals in the spectrum. But the collection of all of those signals would point to this as being the structure.